Experiment 1A. Shear force variation at cut section due to variation of loads and load position. Figure A shows the apparatus we use in this experiment. This is the free body diagram of structure frame for shear force. For variation of load P3 was placed in between D section XX and C as shown in the diagram. The value of shear force at point D section SX will be measured and recorded. The step of measurement will be repeated using different load, that is 100 gram, 200 gram, and 300 gram. For the variation of load position, that means that we apply the same load on different positions of the beam. The load is placed between point A and B in case 1. Then, the load is placed between point B and D in case 2. The load is placed between point D and C in case 3. Graph of shear force measured at section XX with position of the applied load was plotted as shown in the graph 1. From the graph, we can know that the magnitude of load increased, the shear force also increased. Besides that, the graph 2 shows the shear force at section XX against position of applied load from point A. Shear force is always positive when load is placed between point A and B, C and D, while the shear force is always negative when the load is placed between point B and D. There is experimental and theoretical shear force value to compare in both of the graphs. The difference of the values is due to the random errors and parallel errors during the experiment.
In this video, I am going to explain about the shear force test for uniform distributing loading and also the superposition. Before I start the explanation about the shear force test for uniform distributing load and superposition principle, I would like to explain about the apparatus that we are going to use in both experiments, where this diagram has shown the apparatus and the component of it. And this one is called the rolling pivot. This one is also the pivot. And these two are the securing thumb screw. And this section we call it as section XX, where later we have to determine the shear force at the section of the beam. And these black things are the beam, and we will put some hanger and loop across the beam in order to find out the shear force at the section, and we will measure it by using the digital force display meter. Next, we are going to start with the shear force test for uniform distributing load. And in our case, we are going to use the load P with 200 grams, and we will place the first one to the left of the point B with 40 mm, and the other two also, but with a separate distance of 40 mm from the first P. And then we are going to measure the shear force along the section XX by using the digital force display meter. And then we will compare it with the theoretical value by compute the RB and using the moment equation in order to find out the theoretical shear force at the section XX. Next, I will continue with the explanation about how we carry the shear force test for superposition principle. For superposition principle, it states that for a linear system, the net response caused by two or more stimuli is the sum of the response that will have been caused by each stimuli individually. Therefore, easily to say is like mathematics 1 plus 1 equals to 2, that we have to show that the shear force caused by case 1, case 2, and case 3 should be equal to the case 4. And according to our data, in the case 1, we are going to put the load at the 60 mm to the right of the point B, as shown in the diagram below. And then we are going to measure the shear force along the section XX by using the digital force display meter. And next, in case 2, we are going to put the load P at 100 20 mm to the right of the point B shown in the diagram below and measure the shear force at XX. Same goes to case 3. We are going to put the load P at 180 mm to the right of the point B as shown in the free body diagram and measure it with the display force meter. And in the case 4, we are going to put 3 loads simultaneously and locate the first P from 60 mm to the right of the point B and followed by another 2 with 60 mm separate distance between them. And then we will also measure the shear force along the section axis by using the digital force display meter. And we also compare the experiment data and the shear force obtained by experiment to the theoretical value.
Experiment 2. Bending moment at section XX. The presenter, which is me, Nurul Izzati binti Isham. Bending moment is the moment induced in a structural element such as beam when an external force or moment is applied to the element causing the element to bend. The objective of this experiment is to determine the bending moment at section XX and compare the theoretical and experimental values. The apparatus used in this experiment is a digital force display, a simply supported beam at B and C with a lever arm of 125 mm, variation of loads, hanger to hang the loads, and a ruler to measure the distances between points. This is the free body diagram of our apparatus, and here will be the position where the bending moment will be measured. First is the bending moment due to variation of loads. For the first case, to carry out the experiment, we will measure the distance from B, which is 380 mm, and place the first load, which is 100 gram, and take the reading from the digital force display. We then repeat the same step for each loads 200 gram and 300 gram each. From the reading taken, we can calculate the moment at XX by multiply the force with the length of our lever arm, which is 0.125 meter. Then we can proceed to determine the theoretical moment at XX. By taking the moment at C is equal to 0, we can compute the reaction force equation at B. And then we will take the moment at XX equal to 0 in anti-clockwise direction, where the forces acting upwards will be negative and the forces acting downwards will be positive. And then we will substitute the value of our loads, which is 100 gram, by converting it into Newton to find the reaction force at B, and then we will substitute this value into this equation to find the moment at XX. The same steps of calculation will be used to determine the bending moment at XX for 200 gram and 300 gram each. Then from this tabulated data, we then can proceed to plot a graph of bending moment at XX against the magnitude of load. Here we can see from the graph that the bending moment at XX is increased linearly with the magnitude of load. The differences between the experimental and theoretical values may happen due to errors that occur during the experiment. Next is the bending moment due to variation of load position. There are 3 cases for this, where the first case, the load applied is between A and B, and the second case, the load applied is between B and D, and the third case, the load applied is between D and C. To carry out the experiment, we first will measure the distance from point B, which is 100 mm, and place the load. For our case, it will be 300 gram, and take the reading from the digital force display. The same steps will be carried out for the second case, where our distance from point B will be 140 mm, and for the third case, the distances will be 380 mm. Then we proceed to calculate the theoretical value of moment at xx. Similar as before, we will take the moment at c equal to 0 to find our reaction force at B, and then we will compute the equation of where our moment at xx is equal to 0. We then substitute the value of our loads into this equation to find the reaction force at B, then substitute this value into this equation to find the bending moment at xx for the first case. The same goes for the second case. The step is still the same. We will determine the value of our reaction force at B first, and then we will substitute this value into this equation to find the moment at xx. For the third case, the same calculation will be carried out, where we will determine the reaction force at B, and then we will substitute the value of our RB into this equation to determine the moment at xx for the third case. Here will be the final of our data. From this tabulated data, then we can proceed to plot the graph of bending moment at xx against the position of load from point A. Here we also can see the differences between the experimental and theoretical values that may happen due to the errors that occur during the experiment. From the experiment of moment due to variation of loads and load position, we can determine the positive and negative bending by plotting and drawing the shear force and bending moment diagram. Here, when the point load is applied between B and C, we can see from the bending moment diagram, our measured value at xx will always be positive, which is also known as sagging moment. Meanwhile, for this case, when the load is applied between A and B, from the bending moment diagram, we can see that the measured value of bending moment at xx will always be negative. The negative bending moments also called as forging moment.
My name is Muhammad Zikri Mirza bin Nuri Khairuzin. I'm going to continue about bending moment control point. So in this free body diagram, we have two loads. So W is at 140 millimeter from B to A, and load P 40 mm from between DC. So the load of P is 490 gram, and load for W is 300 gram. So this is actually a force that occur in our apparatus. So we can see that the negative W is from the force that have been occur downwards from point A. So it's going to be negative until the B from until A to B is no any force have been occur there until we reach B point. B point we have a reaction force going to upward until at point B have been applied load. So it will be going downward. We go downward and until C. So in down here we have a graph about bending moment. So moment here we can use by find the area, which means A to B is negative 140 W. So it is negative, the value is negative, so it's going to be up. To find area B to D, you can find it 300 VB. It is positive, so it will be go down here until we reach this point. So we can see that D, the intersect between what are the x-axis and this line is intersect perfectly here, which means the moment is equal to 0. Next, in theoretical, we must to find firstly we must to find RB, but to do that, we find the VB equation 1 and VB equation 2. So this is for force and this is for calculation for moment MXX. So we substitute 1 and 2 and we get the RB equation. Next, we find total moment for MC to 0. So until we get P, and we substitute the value of W, and we got the value of 489.975, actually near to our experimental value P. So this is our theoretical. Find P is we got 4.802 Newton. Moment, and then we continue, we find the moment again, moment C equal to 0. Find RB, reaction B, and we get 4.132. We continue to find the moment at XX. Here we can see moment XX is equal to 0. So in this calculation, it's very important where we need to prove that our theoretical which have been proven, which means moment at XX plus W 440 minus RB 300 equal to 0. And it is, we get 0 Newton meter, which means the experiment goal have been succeed.
Okay, I will be talking about experiment 2 regarding bending moment due to uniform distributed loading UDL. So first of all, we need to make sure the digital force display meter was set to 0 when no load was applied. Next, we will apply many point loads where each load has the same magnitude P, and load P must be applied next to one another and on the middle of the meter. And then we will calculate the uniform load. For this one, we need to at least apply 3 point loads with 200 gram worth of mass, and each were located at 20 millimeters from point A and 40 millimeters apart from each other at the left of the section, at the right of the section, section XX. And then we will calculate the value bending moment at D or section XX based on figure 2. Only then we can compare and the calculated value of the bending moment at D in step 3 just now with the measured bending moment at section XX. Last but not least, we will obtain the reaction of RB on point B and RC at point C. And finally, we will the calculated and measured bending moment at section XX was compared.
Bending moment superposition. So for bending moment superposition principle, we have 4 cases. For case 1, we have 1P at 40 millimeter from point B, and we have the distance between B to C is 440 millimeter. This distance is kept constant, but for P, distance between B, we have a different value. So next, case 2, 1P at 80 millimeter. Case 3, 1P at 120 millimeter. And case 4, with different things, we have 3P, this one, simultaneously, and the P is separate with 40 millimeter. So in this table, this is data we have been recorded at, in our experiment. Negative 0.2, negative 0.4, negative 0.6, negative 1.2. So this column is for moment at XX. We've already recorded negative 0.025, negative 0.050, negative 0.015, negative 0.150, and the total is negative 0.3. This is our theoretical moment data we have been calculated. So to do this, we find the equation for RB and we find the equation for MXX. So here we got a total moment for MC equal to 0. So negative RB and 0.44 plus PD equal to 0. We get RB for equation RB. So for MXX, 0.3 RB negative 1.96D. So next we're going to just substitute the value distance here to find RB, and we get RB and distance here to find the moment at XX. So for case 1, we just insert and we get 2.138, and then MSX we get negative 0.025. Same here, case 2, with same technique, and we get negative 0.050. For case 3, also same until we get negative 0.075 millimeter. And case 4, with different things, 0.96 we times 3, which means the 3 loads divide with 0.08 equal to 73.6. And then we find the RB equation first, which means RB equal to WD D2 over 0.44, and then we substitute the value with W we get, and substitute for D1 0.08 and D2 0.52 over 0.44, and we get 6.959 Newton. And then for moment at XX, finally we get negative 0.150. So if we proven in theoretical and theoretical and experimental, we have a perfect value, which means no errors occur during the experiment. Conclusion: the objective of this experiment has been achieved. The shear force and bending moment at particular section XX were studied, and the experimental values were then compared with the theoretical values. That's all from us. Thank you.